Okay, so today we're going to talk about section 8.3, estimating a population mean. Okay, so before we move on, let's go ahead and quickly review what we did on 8.2. So in 8.2, we had a population and we took a random sample from here. We didn't do the population mean, we talked about a proportion, correct? So we did a proportion. So we had a proportion that we were trying to figure out what it was. And we used the p hat that we got from the random sample. Okay, and then we said, well, we could go ahead and we did the confidence interval using the p hat as such. So we did okay. We did this, we also had three conditions that had to be met. It had to be, first of all, it had to be a simple random sample. Second, we cannot oversample. We can only sample up to 10% of the total population. And then we had the large counts, which looked like this. Oops. Missing the parentheses there. These all had to be greater than 10. Okay? So this was what we did in a nutshell. This is what we did in 8.2. Okay? Well, in 8.3, we're going to do the same thing, except we're going to do a mean. So in other words, instead of a categorical data, we're going to talk about a quantitative data. So the categorical data was like, the hair color was a blonde, black, brown, or whatever, right? So it was a proportion, whereas when we're talking about the population mean, we're going to talk about the weight, the height, something that has a number there, right? Okay? So, when we talk about a mean, what we're looking for this guy. Right? We're looking for this guy. We're looking for the mean. We're looking for the mean here. But when we do the random sample, we're going to get an X bar here. And we're also going to get a standard deviation associated with that. Okay? So if you remember correctly, back when we were talking about the mean, we said that the standard deviation here of the sample was this guy, right? We did this, okay? Which is simple, okay? Because now, when we talked about the categorical data, okay, we did not need to know this guy because we had this equation right here, okay? So this is the problem. This is the problem with the population mean. The population mean is that we are very seldomly going to know what this guy is. So if we don't know this guy here, we can't use this. Okay? Since we don't know this, we can't use it. Okay? So we're still going to have to use this, the standard deviation, somehow. Okay? But we're going to have a correction factor that is not going to be a z star here when we had the critical value here. So what we're going to end up using we're going to use the X bar, obviously. This is an unbiased estimator, okay? And then we're going to use, so we're going to use this guy. We say we're going to use this guy somehow, right? And we're going to use this guy, all right, because we still have we did do a sample of n, okay? So instead of using since we cannot use a normal distribution anymore, okay, we're going to introduce what is called the t distribution. So we're going to get a critical value from the t distribution, okay? T distribution is also called the student t distribution. And the reason being is because the guy who actually developed the t distribution was a guy who worked in, of all places, the Guinness Brewery in Ireland. And he was kind of skeptical as far as how his research was going to be accepted, so he used a pseudonym. He didn't use his real name, which was Gossett. The guy's name is Gossett, so he just used the name, made up a name called student, and he called it a student t-distribution, okay? And that's why it's called the student t-distribution, okay? If we have a normal distribution, as we all know, looks like this. Symmetrical across the mean here, right? Symmetrical across the mean, okay? So this is a normal distribution. The t-distribution actually looks very similar to the normal distribution, but it has a fatter tail. In other words, if you took the normal distribution, the black guy here, and you kind of squished it down, you're going to end up with a t-distribution. So it has fatter tails, okay? All right. So just like the normal distribution, the t-distribution has an actual table. So if you go in the back of your book and on page T-3, there is a thing called the t-distribution critical values, and that's exactly what we're going to use, right? Remember, over here we had x bar plus or minus the t critical value. So this is the table for this guy right here, the critical values of t. Okay? If you look at that table, on the far left column, there is a thing called df there. It's called a df. This is the degree of freedom, and it is defined as such. You take your sample size, so you subtract 1, and you're going to use that. Okay? So let's say that I wanted to find my t critical value for 0.05. Let's say 0.05. So I want this guy here to be 5%. Right? 0.05. And I had a sample size of 10. So my sample size is 10. Okay, so let's go to the, if you go to the table on T3, you're looking at 0.05, so 0.05, it's in kind of a little left of the middle there, 0.05, and you're going to use degree of freedom is 9, right, because the n was 10, which means the degree of freedom is n minus 1, so it's 10 minus 1, which is 9. If you look there, you're going to look up, it's going to be 1.833. Okay, so that's how you use this thing, okay? If you look down at the degree of freedoms are pretty good except until the 30, but after 30, then it goes 40, 50, 60, and 80, 100, and 1,000, okay? So, what do you do if you have a sample size of 75? So if I have a sample size of 75, I get 75 minus 1, which is 74. So my degree of freedom is 74. If you look there, I do not have a line for a 74. I have a line for a 60, and I have a line for 80. Okay? You are always going to round it down on the t-distribution table. Okay? So you're going to have to use the degree of freedom of 60 there. So you would use 60. That's the line that you would use. Okay? So you're always going to round down when it comes to degree of freedom, and that's to be conservative. All right? Now, obviously, all this stuff actually is in your calculator, and the way you would use that is you would use the inverse t, okay? And for here, you're going to put what? So I was looking for 0.05, 0.05. I'm going to put a degree of freedom of 74, and if you do that, you're going to get a number right there. You don't have to use your table, okay? So you can do that also. Okay? So let's go back. So we got that. Okay, we did that. Okay, so if you look on page 529 bottom, there's a green box there that says the one sample t interval for the population mean, and it has this guy right here. And we're good there. Shows you how to do the critical values. We did the inverse T on page 531, so we're good with that. So there are conditions that have to be met, okay? Just as though when we did the proportion, okay? Same thing here. When it comes to the mean, you have three conditions that have to be met. So what were the three conditions that we were looking for when we were talking about proportions? When we were talking about proportions, we had three conditions that we were looking for, right? The first one was it has to be a random sample. Second one was that you cannot oversample. And then the third one was this guy, right? Well, okay. The only thing that's going to change for the population mean is this, because you do not have the P anymore, right? You don't have that anymore, okay? We're simply going to say that your sample size has to be greater than 30, okay? So these are the three conditions that have to be met for you to be able to do to estimate the mean, okay? And that's on page 533. It says conditions for constructing a confidence interval about a mean, and there are those three things right there, okay? So let's see if we can do example GPAs, wood, and SATs together. Okay, determine if the normal large sample condition is met for each of the following situations. Let's go A. To estimate the average GPA of the school, you have selected 50 students. Here's a histogram. So is that going to satisfy the large counts? It should, right? Because n is equal greater than 50. So the answer is yes. Okay. B. How much force does it take to pull wood apart? The stem plot shows that the force in pounds par for each of 20 randomly selected pieces. Okay. Well, the random selected, that's just good, but your n is not greater than 30, so you cannot use the estimate to do the of the mean, all right? Because it does not satisfy the large counts here. Okay. C. Suppose you want to estimate the mean SAT math score with large school, random sample of 20 students in the school. Okay. So even though okay, so let's go back on B. If you go back to B, what do you see? You have if you look at the stem plot, what does the stem plot look like? The stem plot is skewed, right? It is skewed to the left, actually. It's skewed to the left. Okay, it's skewed to the left, so you cannot use that. If you go on number C, it is less than 20, but it is not skewed. Okay, it is not skewed, or there's no outliers, so you can go ahead and use it. Okay, so the large counts is that when you are at greater than 30, okay, you're good to go. If you're less than 30, let's go ahead and write this down. If you're less than 30, you're looking for no skewed and no outliers. Okay, again. That is on page 533, the top green box there. Okay? And we will call it a day today.